Hello dear student, welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today we are going to discuss about the module of high resolution transmission electron microscope and their basics with the paper Nanoscience and Technology 2. After going through this module, you shall be able to learn about the historical background of electron microscope, know that high resolution electron microscope working, and few basic processes which shows how electron interacts with matter and what kind of information you will get. We will also know the construction and working of TEM, how images are formed, and how this phase contrast will develop and their application. Electron microscopy has revolutionized our understanding of materials by their structure properties correlation down to atomistic level. It is now even possible to tailor the microstructure of material to achieve a specific set of properties. The extraordinary ability of modern transmission electron microscope to provide almost all the structural, phase and crystallographic data. TEM is a technique of characterizing material down to atomic limit. In order to find out exactly what new material we have made and how perfect it is so that we can improve our synthesis method, this new synthesis method must be accompanied by atomic scale compositional and structural analysis. The transmission electron microscope has emerged as a perfect tool for this purpose. It can now give us atomic resolution image of material, their defects, together with spectroscopic data and diffraction pattern from some nanometer regions. The past 50 years has been a wonderfully exciting time for electron microscopists in material science with a very continuous and rapid advancements. From the development of the theory of Bragg diffraction contrast and the column approximation, which enables us to understand TEM images of crystals and their defects, to the theory of high resolution microscopy useful for atomic scale imaging, and on into the theory of all powerful analytical modes and associated detectors such as X-ray, cathodoluminescence and energy loss spectroscopy. Discuss the introduction and historical background of electron microscope. Microscope is nothing but made up of two words, micros and scope. Micros means small, scope means to look at. So microscope means to see a smaller object. Nature has given a beautiful scope to us, which is eye. Eye is so beautiful that this can very easily focus from smaller distance to longer distance. But the problem with our eye is that it cannot resolve less than 0.2 millimeter, and therefore scientist has developed a new microscope which is known as light microscope or optical microscope, where the resolution is around 0.2 micrometer. This all happens where source is visible light. But in case of developing a new microscope the scope is over because we cannot resolve better than 0.2 micrometer with light microscope. So we have to find a new probe for developing microscope. Since light is an electromagnetic wave, therefore the natural choice is X-ray or gamma ray. But why X-ray and gamma ray based microscope has been not developed and electron based microscope has been developed? This is a very important question. So the answer is the development of high performance lenses necessary to focus the beam to form an image do not exist for X-ray and gamma ray. As we know that in case of our eye, there is an object and our eye has a lens which form the image, which is therefore a lens is required to bend the beam. And in our intermediate class, we have studied that electron direction can be changed by applying a perpendicular magnetic field in that beam of electron. So if a charged electron beam is passing through perpendicular direction to the magnetic field, then it follows the path in circular fashion, and means that there is change in direction and focusing of electron is possible. Now, as we know that electron is the choice, that how this electron revolutionized the development of microscope. So a revolution came in the year of 1927 when Hans Buss showed that electron can be focused by magnetic coils. Very fast, in 5 years, a first TEM was developed by great scientists Ernest Ruska and Max Knoll. We know that electron is a particle, so the wave nature is required for development of electron. In 1923, de Broglie showed that every particle has a wave associated with them, and therefore with the relation lambda is equal to h upon p. If we accelerate our electron beam with a voltage V and we assume that all energy is converted into kinetic energy, in that case the total energy EV is equal to half mv square. If we solve this equation, we end up a wavelength lambda is equal to h upon 2 mev to the power half, where h is the Planck constant, m is the mass of the electron, E is the charge of the electron, and V is the voltage applied. And therefore, we are ending with wavelength having electron. Since this electron is accelerated with a very high voltage, for example 100 kilovolt, therefore the velocity of this electron will be 0.6 to 0.9 c, which is the velocity of light, and therefore a relativistic correction required, and finally the equation turns out to be lambda is equal to h upon 2m ev 1 plus ev by 2 m0 c square to the power half. I want to give a relation between wavelength and applied voltage. If we apply accelerating voltage of 1 volt, the lambda is around 12.26 angstrom. For 100 keV, this wavelength is 0.037 angstrom, which is well below than our visible light wavelength and required for imaging. When a beam of electron will fall on the sample, what is the interaction happens? Incident beam, which is shown by red, is fall on a thin sample of 1 to 100 nanometer, and as a result there is a direct beam and elastically scattered electron come out, which is transmitted and involved in image formation of transmission electron microscope. There is many other things happening. For example, inelastic scattered electron, the mushroom X-ray are coming out. Not only that, there is a secondary electron ejected, characteristics X-ray will come out, visible light is possible to come out, back scattered electron, agar electron, these are all electrons are coming out. So this interaction will give us a strong interaction between electron beam with sample. I want to show the first microscope which is built in Berlin by Ruska and Knoll, ending a Nobel Prize to Ruska. Here I want to say that the process of image formation is very similar to the optical microscope. This slide suggests left side with the optical microscope and the right side electron microscope. You can see that illumination is taken place with lamp in case of optical microscope and electron in case of electron microscope. And we need condenser lens because the beam which is coming out should be condensed, should be parallel, and therefore we need a lens. As we know, in case of optical microscope, we need a glass lens. However, in case of electron beam, we need electromagnetic lenses because only electromagnetic, in direction of magnetic field, the electron is change their path, and therefore a development of electromagnetic lenses happened in case of electron microscope. Then we put the sample, we have an objective lens where all the information will focused, and then we have a first image form, and then we have a projector lens which magnify the image and we can see by ocular, and in the case of electron microscope we need a fluorescent screen because we cannot see the electron beam. So this way we can image our samples. Here I want to discuss the TEM imaging mode. The figure suggests that diffraction pattern is produced in the back focal plane of the objective lens. The selected area aperture that is inserted in the image plane defines the area from which diffraction beams are transmitted to intermediate and projector lens. This will give the diffracted spot in our projector lens. The intermediate lenses are adjusted to either focus on the objective image plane or back focal plane. They also define magnification and camera length, which is the essential part for getting diffraction indexed to get the information about crystal structure. The gun which produces electron beam. So there is a three possible gun. One is tungsten, first one, the second one is LAB6, and third one is field emission gun. I want to discuss their advantage and disadvantage below. If you see the maximum current in case of tungsten, LAB6 and FEG, then it is 1000, 1200 nanoampere. The most important thing is its brightness. You see, brightness is, if we normalize it, then in the case of tungsten, if it is 1, LAB6 it is 10 to 30, and in FEG it is 2500. So brightness is very high in case of FEG. Therefore, this is very good in case of brightness. But let us discuss the price in the last column, where the tungsten price is 1, then LAB6 price is 10, and FEG price is 100. So it is very costly affair if you want to have FEG gun. It is a matter of money available, then one can choose tungsten or LAB6 or FEG gun based on their requirement and money available. Based on this gun, you have, as I have discussed, the FEG is the most brightest one and very good for high resolution imaging. However, the price is, we have to pay the price for the same. Vacuum required in case of tungsten is less, for example 10 power minus 4 torr. However, in case of FEG it is 10 power minus 8 torr. So management of vacuum is also a issue in case of field emission gun. Lifetime is also plays an important role because the lifetime of field emission gun is highest in comparison to tungsten and LAB6. As I discussed in earlier slide there, that we need electromagnetic lenses. In our system we have condenser lenses. We need two condenser lenses to focus our beam, the first condenser lens and second condenser lens, and then we need a aperture because we want that a fixed amount of beam should pass through, and therefore we required a condenser aperture. Then after that we put the sample and put an objective lens. This objective lens, all the information of the sample will condense there, and then we put again objective aperture because depending on how much area of the sample I want to visualize, we put the different aperture. We put another objective aperture which is known as second objective aperture, and then we put intermediate lenses and then projector lenses to magnify the sample, and we see the magnified image. I want to discuss that how they looks like. The gun, the condenser lens L1, the condenser lens L2, the objective, intermediate lenses and projector lenses, and finally fluorescent screen. The structure of magnetic lenses is shown in right side, where we have a coil has been introduced so that we produce a strong magnetic field there and will used as a magnetic lenses. I want to discuss about SEM specimen, how one can prepare this specimen for seeing this in microscope. For that we use a grid which is called copper grid, and this copper grid can be placed in a bar which is shown here in the figure. This grid is of 3 mm small diameter, thin around 100 to 500 nanometer, and for biological samples we have to frozen it, tissues and all can be used, whereas for materials we have to make it very thin powder or electrospinning so that electron can pass through the sample. I want to discuss more detail this TEM grid. So here you can see that there is a copper grid with a mesh 300, and this copper grid can be used a layer of polymer which is called formware, so that the small amount of your sample should stick on the formware. In next image one can see that there is a sample lying down, and this can be imaged inside the microscope where you have grids, and on top of that there is a formware film and very small black spot samples. If you zoom it more and more, then you will end up getting nanoparticles, which is shown in this figure at the end, where a small nanoparticle with the resolution of 20 nanometer has been shown, where one can see that the very small tiny nanoparticles is resolved, which is the beauty of transmission electron microscope. Transmission electron microscope is basically a multi-purpose machine. One can find out diffraction study, will tell you the atomic structure, lattice parameter, orientation, high resolution, TEM. On top of that, we can find bright field images and dark field images by which we can study their microstructure and defects. And one can also do chemistry by energy dispersive X-ray microscopy analysis, which is called EDAX, or electron energy loss spectroscopy, which is called ELS. So in this way, TEM is a very multi-purpose machine where one can find out their microstructure, defect, atomic structure, and chemistry. I want to discuss the high resolution transmission electron microscope, that is called Hrtem, where one can resolve atoms. The resolution is around 0.5 angstrom. Resolution at high magnification gives you the structure information and micro analysis. Dear student, here I want to explain the working of TEM and their cross-sectional view. One can see at the top we have an electron gun. Below that we have a anode which accelerates this electron beam, and just below that we have gun alignment coil which align the electron beam in the direction of which we required. After that we have gun airlock, which is required because in this system is inside the vacuum, and if we load the sample in that time, we don't want to hit this air to the gun. Therefore, gun airlock is used. After that, we have another condenser lens which condenses the beam to make it parallel to the sample. After that, we have an aperture which allows only desired beam to the sample. Then we have an objective lens. Below that we have our sample which can be placed using sample holder. After that we have a diffraction lenses, intermediate lenses, and projector lenses. These lenses have their different working. Based on that, we will image our sample in transmission micrograph, and a magnified view can be seen on the projector lenses. One can also see our sample by binocular. At the end, we have a 35 mm film which record the image in this case. Nowadays, we have also CCD camera where our image can be stored. Now, I want to play a video which will explain the things in more clearly. There is a possibility of developing contrast image. Using bright diffraction condition, electrons, we can generate diffraction pattern which has crystallographic information. Bright field images gives the information about morphology. Dark field images gives the correlation of crystalline phases, orientation of grain morphology, distribution with microstructure, and defect structure, etc. Phase contrast in Hrtem, crystal thickness with a given orientation affects phase and amplitude of the beam in a complicated way, and direct and diffracted beam has a phase shift. With that, mixing of information from the sample and microscope was via interference will develop a high resolution image, and a projected amplitude after interference will get the final output. Now I want to discuss the application of TEM. As I discussed that this is a multitasking machine. So the transmission electron microscope is used to examine the structure, composition, and properties of a specimen in submicron details. Aside from using it to study general biological and medical materials, transmission electron microscope has a significant impact on the field such as material science, geology, environmental science, among others. Image morphology of samples, for example, viewing sections of material, fine powders suspended on a thin film, small whole organisms such as virus and bacteria can be done using this method in transmission electron microscopy. Analyze the composition and some bonding differences through contrast by using a spectroscopic technique, microanalysis and electron energy loss spectroscopy. So friends, let us summarize what we have learned in this module. This electron microscope, what are the basic history behind that, how it is developed, what are the source, for example here we use electron and why we have chosen electron, this we have learned. How this electron works as a wave and what are their wavelength, this we have learned in detail. This electron microscope can be used for crystalline sample as well as amorphous sample. One can use to identify phase, orientation, crystal structure, and these data can be correlated to their nanostructure features in the TEM images. Developed by interference of two waves, one which undergoes a phase shift due to the interaction with the sample crystal structure on a given thickness and is altered by the microscope aberration. So therefore, we are in position to say that transmission electron microscopy is a very versatile tool to understand the structure of a material, not only that, their composition and all spectroscopic technique like EDAX and EELS, which is the additional detectors used, can give us a very nice understanding of material at atomic scale. Thank you.